Good evening, everyone. So, welcome to this week 10 discussion class for Design of Photovoltaic Systems. This is the course which is being taken by Professor Alumanan from Department of Electronic System Engineering, ISC Bangalore, and I am Ravi Kumar, a PMRF research scholar at IIT Bombay. So, till now, what we have seen, we will have a look first. We have understood PV cell, PV system, including their characteristics. Then we have also seen integration of battery. After that, we have seen Peltier system in the last class. Using PV. So in this class we are going to see the water pumping system using PV. So this is a basic application of solar PV system, usually in our home and also in the agriculture field or land. We use this solar PV to run the water pumping systems. Yes. So first understand what are the components of this water pumping system. So we should have a motor with pump, then we should have a solar PV module or array of module. Then by integrating these two things, our system will complete. So let's start by understanding what this pumping system is. So this is usually we have a motor. So the principle, or we can say the application of this motor is just one thing. If we have an electric current going inside, it will rotate this shaft. This is the working of an electric motor. Then we require something which can make the water to flow or create a pressure difference, because water only can flow when there is a pressure difference. So for this we have a pump. So this is centrifugal pump, and if we connect both, it becomes a water pump system. Like for integrating with the PV, we can see it here like this. So this is a motor with pump. First understand these things. The input to this motor, or we can say pump, is coming from solar PV. So this is the input side. Now current is coming from the solar to this electric DC motor. It is rotating the shaft. Due to rotation of the shaft, this pump is creating a pressure difference P1, P2. So there is pressure difference delta P, that is P1 minus P2. And if there is a pressure difference, this pressure difference will create water to flow from this to this, and it will be collected in some reservoir. So to calculate the need of solar PV system required, what we do? We calculate the energy, or we can say this head, this one and this one. So it is just a difference between the level of water. Here we need to take this water from this level to this highest level, and this is like inside, or we can say inlet side. So usually it is known as suction head, and it is discharging side, means water is being discharged to the reservoir, so it is known as HD, that is the discharge head. So total head will be the HS plus HD, suction head plus discharge head. And also there is another term, that is friction head. So can you just tell me what are the causes of this friction head? You can write in the chat box. What might be the reasons for? Okay, let me ask you one question. If this is a water pump, or water coming from a pump at a particular pressure, and you have a pipe, let's say 5 kilometers long, and then some pressure is coming out. So the pressure which is going in, let's say in, and pressure out, will it be equal? P in will be equals to P out. It means our water is like it is crossing a pipe of 5 kilometers long. It means 5,000 meters long. So will there be any loss of this pressure? Yes, because there will be some kind of friction inside this pipe, and due to this friction there will be loss of pressure, and this loss of pressure we also include in our calculation, and we say it friction head, and then total becomes dynamic head. It is suction head, discharge head plus friction head. Okay, so now let us understand how we calculate this energy required. Like if we need to take this water from this point to this point, so how much energy we require? So we will understand here. Let's say there is a body M, we need to take it at a height of h, so the energy required will be mgh, formula for potential energy. So here it is the energy which is stored in this mass if we are putting it at a particular height. Then for water, how can we calculate? We will just replace this mass with the density and volume, because our water is liquid. So we will have this rho and Q, and then we have rho Q GH is the formula for energy. So if we are taking water from, let's say, ground floor to third floor in a tank. Let's say this is a water which is going from ground floor to third floor. So the height of third floor multiplied by rho, G, H and Q will be the total energy stored at this particular point. It means if you will discharge this water, we can get this much of energy. Or in another term, we can say this is the energy which has been spent in taking this water from ground level to the third floor. So this is all about the hydraulic energy, but here it is given in joules and we are like working in kilowatt hour, let's say unit, because in the solar PV system we are also calculating everything in kilowatt hour, so we will convert this in kilowatt hour as well. So if we just rho is fixed for water, that is 1000, G is this one, Q and H is the property of water which will be taken. Q is the we can say the volume and H is the height. So this is the formula for our energy. If we convert this into kilowatt hour, so using this unit conversion simple, we will have this. It is in kilowatt hour energy requirement. And here this Q is in meter cube. Now we also further need to convert it into liter. So further by converting it meter cube into liter, we can have this final formula as mgh for the water. So this is all about the hydraulic energy, how it is transferred to a water which is taken from one place to the another place. There will be pressure drop. Yes, Vikas, right. In the pipe one, yes, it will be. Okay, let's go next. So it is all about the hydraulic energy. Now let us talk about the hydraulic power. So what is the relation between power and energy? Relation. So we can say energy per unit time, we say power. So here also similarly dE by dt, so rho g h q by dt, that is the time, we will get this particular formula for hydraulic power. So here we are having in per unit time everything. That's why this Q volume we will be having in, let's say, meter cube per second. And this is converted into liter, same thing. Now we understood that this dynamic head determination is important, but how can we determine this dynamic head while calculating for a solar PV, or we can say this hydro system? So let us consider one example here. This is the water pump. Water is being taken from this point to this point maximum. So total head will be this suction head plus this this suction head plus this HD means discharge head. So it will be a combination of both. So now let us understand one more thing. I am giving you one example. Let's say our pump is here and water is being taken like this to this reservoir. Now what will be the head? Here you can understand it. So in this case, this is our HS, that is a suction head. This is our discharge head. But see one thing, I told you this total head will be the difference between the initial to the final height, we can say. So from here, initial to the final, this should be our total head, and this total head will be equals to this head minus this head. So it will be HD minus HS. So it means while calculating this head thing, it is not compulsory to add both the heads. Sometimes it may be necessary to take a difference, or we might need to be subtracted one head from the another head. Now how can we calculate this dynamic head? So for this dynamic head, this is just mgh, and then we have this hf, that is a friction head, and this friction head is given by this Darcy-Weisbach formula. Here you can see these are the like friction factor, length of pipe, inner diameter, velocity of fluid. So these are the parameters on which this friction head depends, and it can be for two different fluids, like laminar fluid and for turbulent fluid. So for laminar we can use this formula directly, for turbulent we can use this formula directly. We will use this formula while we will be solving the numericals. Here just you need to understand how we calculate this head thing and what are the different formula we have. Now let's come to the type of pumps. What are the types of pumps we have? So we have centrifugal pump and we have reciprocating pump. So here you just need to understand the working. So how it works? How to calculate F when flow is turbulent. Yes. For this turbulent, we have this Colebrook-White formula. Using this formula, we can calculate this friction factor. Yes. F is connected because F is here and F is here. So in these types of equation, we have many methods, numerical methods. Using those methods, we can solve this. We can take iteration, like Newton Raphson is one of the method. You can refer those methods. Even if you will, what are the equations are known as? Yes. In the exam, how do I do iterations? It is simple formula. I'll tell you, I'll give you the link even as well. So it is a simple formula. By taking the calculator, you can do the iteration. It is like taking the differentiation and then one differentiation value from one differentiation you will put to the another differentiation. It's like that. Okay, so I was talking about the centrifugal pump, reciprocating pump. So in this particular thing, this is the rotation and this is generating a centrifugal force which is making this pressure difference, delta P. And in this case, reciprocating pump, this particular thing is rotating like this, and due to which this particular, we can say, this particular part of this unit is moving forward and backward, and due to this particular movement, like if water is coming from here and it will go this way, then water will go out from this way. So it is continuous process. It is coming in, down, coming in and going back. So this is the reciprocating pump. Usually we use this centrifugal pump, that is easy to use. Okay, so it is all about the water pumping and what are the things we have, how we calculate water head and all. So how do we integrate this with the solar PV water pumping system? So we have our solar PV system, then we use DC-DC power converter, then we connect a motor, which is motor is connected to the pump, and this pump become a hydraulic system. Hydraulic system means pump, piping and all. So these are the things which are connected to this pump. So if total, we can say power is here PH, so we will consider all the efficiency of pump, efficiency of motor, efficiency of this converter, and then we will calculate the overall power requirement from this solar PV system, because in every step there is some loss. So this is just all about the integration of solar PV with this water pumping system. Okay, so one of the most important application of this solar pumping system is as a storage. So usually what we do, we have battery, that is the DC battery. So what we do, we have solar PV, we take electricity in the daytime, we take electricity in the daytime from this solar PV system, or we can say solar PV module. We charge our battery. At night, when there is no sunlight, we utilize our batteries to power our like equipments, or we can say to power our houses. But there are another method as well. So this solar PV water pumping system also can be used as a storage method. How? Like this. So if I draw a line here, in daytime and in night time. So here you can understand one thing. In the daytime, it is giving current to this motor, it is rotating, it is giving water to this particular reservoir. So water is coming here. So before night, the friction loss is 70%, loss in water. Should we multiply to calculate power from the PV command? No, you should do one thing. Power at output, let's say this P, then you will, friction loss is 17%. No, you will divide it like this, 1 minus 1.7 into 1 minus 0.2. You will divide it. Yes. So in the night time, what will happen? This our storage is full, and then we can take water from here. By taking this water, or from the pressure of this water, this turbine will rotate, and this turbine rotated will be connected to a generator. We can say generator, and there will be some power. So it is same like hydro power system, but it is at mini scale, so it is known as micro hydro, pico hydro systems. So this is also an important application of this solar PV water pumping system as a storage. Okay, now we will solve few simple questions. Be careful while reading the question and solving them, and so try to solve them. So first question says, a water tank of 1000 liter capacity is located at a height of 10 meter. Calculate the energy stored in the water tank at 80% of water capacity in joules. Value of this gravitational acceleration constant is 9.81, and these are the options. Solve this and let me know the answer. Question is saying water tank capacity equals to 1000 liter, height 10 meter, G. Okay, Vikas have given the answer. 9.81 meter per second square. So we know the energy stored will be equals to mgh. So in case of water, we know 1 liter equals to 1 kg, because rho is 1000. So we can take this 1000 into 9.81 into h, 10 meter. But there is an important factor as well. I am writing question mark here. So this question mark will be the capacity. It is saying 80% capacity. So we will multiply by 0.8. So it will be like 1000 into 9.8, 1 into 10 into 9. Sorry, 0.8, and then you will solve it, you will get the answer. I hope this A is the correct answer. Let me also calculate, others are not calculating. Seven eight four eight zero. Yes, absolutely correct. 78480 joules. A. Yes, A is the correct answer. Okay, let's move to the next question. Question 2. So it is based on the question 1 only. It says the water is discharged to turbine. So it means now we are utilizing it night. We are using it as a storage system. So the water is discharged to turbine generator set at the ground level. A PVC pipe at a 10 liter flow rate is given. Flow rate 10 liter per second. What is the power delivered to the generator terminal under the ideal condition in watts? And these are the options. Do it. Solve it. So it is asking our energy was mgh energy. So power will be dE by dt. So if I do dmgh divided by dt, so it will be G will be constant, H will be constant, so we can say GH dm by dt. dm by dt is the flow. This is gravity G, that is 9.81. This H is given 10 meter, and this dm by dt is the flow rate, that is 10 liter per second. So we will get this like this, 9.81 into 10 into 10 in what? How much? B. 981 volt. Yes, B. Correct answer is B. Okay. So the question you were asking I think who was asking about this? Mohan. Yes, now you will understand the same question what you are asking about the friction loss and all. So question 3 says, if the power loss in the pipe is 10%. Okay, in the last question, see, the question is saying in ideal condition. It means friction loss is 0. Efficiency of this generator is 100%. So these are the ideal conditions. Now it is saying there is a loss, power loss due to friction equals to 10%. 15% in the turbine generator set. There is a loss in turbine generator set, that is 15%. Then what is the power value measured at the generator terminals? So our power without loss was 981 watt. It is asking if there are two losses in the system, then how much power will be, and these are the options. Some question is that's fine. See, if there are meter cube per second, you need to convert it. Like 1 meter cube is 1000 liter water. You need to use this formula. Meter cube is also a volume and liter is also a volume, but there is a relation between this meter cube and liter. In question it may be in liter, it may be in meter cube. You need to see the units and do the work accordingly. Okay, Vikas said C. Okay, let's check. 981 into 1 minus 0.10 into 1 minus 0.15. So how much it is coming? Point 9 into 0.85 into 981. 750. Yes, Vikas is right. It is 750 watt. 750 watt is the correct answer. Okay, let's move to the next question. So this next question is easy. You need to understand things better. It says a PV panel supplies power to a DC generator coupled a hydro turbine set through a step down chopper. You just understand this is a DC-DC converter. The chopper is operated under the MPPT condition. The armature resistance and the armature inductance of DC generator is 0.6 ohms and 1 micro. This is the I think Henry. I forgot it. Okay. So this mH is the unit of this inductance. Then suppose the voltage at the PV terminals is measured as 220 volt. In that case, PV power is 520 watt at the maximum power point. And the chopper is operated at 60% duty ratio. We can say the DC-DC converter. A DC generator is used as a motor to transfer the electrical energy to potential energy. Calculate the induced EMF in volts. Assume the motor current is constant. We just need to find out the EMF of this in motor. And these are the options. So I am just making a diagram if you can understand better. This is a PV system. It is connecting, let's say, DC-DC chopper. PV. Configuration DC generator. We can say generator side, this one. So it is saying this voltage is 220 and here resistance is 0.6 ohms and inductance is 1 micro. Suppose the voltage period is 220, the PV power. So PV power here, P this side is 1520 volt. And here duty ratio is given as 60%. A DC generator is used as a, this is a generator which is used as a motor to transform the electrical energy into the potential energy. Yes. So like a see DC generator and DC motor, both are, we can say, the same device can perform the both tasks. If we are giving current to it, it will work as a DC motor. If we are rotating it, then it will work as a DC generator. And what you need to calculate? EMF here in this particular EMF. So what all factors you need? You need voltage, we can say here, and I'm writing A like armature, we can say that before the motor armature. And then also I need voltage in this coil. Voltage in this coil will be V equals to IR. So what is R? We know. What is IA? We don't know. What is VA? We don't know. And chopper, there is a relation, direct relation with this chopper, with this DC. So voltage here V1, V2. So it will be like V2 will be duty cycle times V1. So our V2 will be 220 into 0.6. How much? 132 volt. Yes, V2 is 132, right. Okay, because I have given the answer D. Okay, let me check. And then I2 will be, first, what is the I here? I1. We can say I1 is 1520 divided by 220. And if voltage is dropping, current will increase. So here D will be like this, 0.6. So how much it is coming? I guess 1520 into, not into, divided by 220 divided by 0.6, 11.51. Why I'm like dividing it here, multiplying it here? Because it is the system, like power here should be equals to power here. So our current is coming 11.51. If I put it here and put it here, I will get EMF as 0.6 into 11.51 minus 120. Yes, 125. Yes, Vikas, right. 125 volt. D. Correct answer here is D. Okay, let's move to the next question, which says the capacitor bank is connected to the terminals of a stand-alone induction generator. Induction generator means there is no permanent magnet. Then we know this as a, why are we not, so it won't be much high. And also it is like we are saying for the DC thing, then the inductance will be 0 for our case. If we will convert it into AC, we can say if there is some generator which is making it in AC, then inductance will come into picture. So in this in this induction generator, there is no permanent magnet. So it is asking what is the role of this capacitor bank. What is the capacitor? Which holds some charge or current. That is the capacitor. So it is asking why an stand-alone induction generator have a capacitor which holds charge or current. And these are the options. Whatever I told you, if you understood it, you can give me the answer right away. Okay. No one said one. Yes, even that's correct. Because we need to produce magnet, so we need magnetizing source. So it is a magnetizing current which is given to this IG induction generator. Yes, A is the correct answer. Let's move to the next question, which says a ballast load, you can say like dummy load. Is used along with a stand-alone induction generator. Why it is used as a, why we have a dummy load inside an induction generator? So this question is not right. Yes, that is the question. That is the question here. Yes. See, this is the stand-alone system. It is not connected to any grid. So it means no reference point. Reference point for what? Frequency or voltage. So if there is no reference point, this induction generator itself have a dummy load. Dummy load, and these loads regulate frequency, or we can say voltage. So in this case, for startup no, for better flux control no, to maintain frequency yes it may be, for maintaining frequency inversely proportional to the load. It is not any relation here, irrespective of the load. Yes, whatever load we are connecting, it make the frequency constant. That is the rule. Okay, you are asking what load we connect. So we have some electrical load only. I think some another things we have. Some electrical load using resistance or inductance, a combination of those. But the application of this load is to maintain the constant frequency. Okay, next question, it says as the intensity. See, this question is the simplest question, and this thing you have understood even in the first class. So you need to give me the answer without any issue. So as the intensity of the light incident on a PV cell, it is saying if this is a PV cell and this is a light, and if the intensity is increasing, what will happen with the IV characteristics? If this is the IV characteristics, what will happen with this IV characteristics? And these are the options. Will it towards this one, this way, or this way? These are the four options. Okay. Mohan said upwards. Yes. Yes, definitely. Because with increased intensity, our current will increase, so it will go upward. Right answer is upward. Okay. Next question, which says a centrifugal pump is required to pump water to an open water tank that is 4 kilometers away from the location of the pump through a pipe. Pipe diameter is 0.2 meter and Darcy function factor is given 0.01. The average speed of water in the pipe is 2 meter per second. If it is to maintain a constant head of 5 meter in the tank, neglecting the other minor losses, then absolute discharge pressure at the pump exit is, so it is asking the P at exit. And these are the options. To at least try this question. Try this question, give me a few minutes. See, first understand what are the things is given. The length 4000 meter. The diameter 0.2 meter. The velocity 2 meter per second. And what are the things given? Friction factor 0.0. So these are the quantities which are already provided in the question. So first we need to calculate this head loss due to friction. So our head loss due to friction will be, so first need to calculate head loss due to friction. So this HF will be, we have simple formula. This is the formula already given, V square divided by 2 So just put the values here and find out this friction head. Find this and then simple our pressure will be rho GH, and this H will be rho G, our HF plus H plus head due to water thing. This is the friction head, and this H is the due to atmospheric pressure. So you need to connect all the heads. One more thing is given, na constant head H equals to 5 meter. So what we have, all the things which require, everything is here. You just need to solve this. What is this F 0.01? What is L 4000? What is velocity? 2 square divided by 2. What is the value of G? 9.81. And what is this D? Diameter? Yes. Vikas said HF is 40.77. Okay. I'm also solving this. Let's see. Zero point 0.01. I'm doing this 0.01 into 4000 into 4 divided by 2 divided by 9.81. Yes, you are right. 40.77. So now, what is the value of this row? It is 1000. What is the value of G? 9.81. So we have both value. HF is given here. This H is already given here. What is left? H due to atmospheric pressure. And this H due to atmospheric pressure, 1 atm in terms of water pressure will equals to 10.3 meter of water column. So we have a, let us understand this way. If we have a water column of 10.3 meter, so this water will have a pressure of 1 atm. So it is 10.3. Now do one thing, rho G 40.77 plus 5 plus 10.3, 1000 into 9.81 into, what is the summation total? 40.77 plus 5 plus 10.3, 56.07. What is total answer? Because said D. Okay. 56,000 it is coming 55046. So we can say 5.5 into 10 raised to power 5 Newton per meter square, which is equals to 5.50 bar. Just converting the unit. Yes, you are right. B is the correct answer. What is the dia of water column for ATM? I think it is standard. See, I'm just telling you this is the way, in a crude way. The diameter you need to check what is it. But if you will see for the head calculation for 1 ATM, this will be the 10.5 meter water column. So I think it also comes from the volume as well. And if we consider this question, so here the diameter was 0.2. Let me check if there is some information about the diameter. So in this question, we need to take it for the 0.2. No, it is like we say 760 mm of Hg. So it is similarly 10.3 m of water. Same. What is the diameter when we say in the Hg? Further you can look up for the internet. But for the one ATM we usually take this head as 10.3. Next we have one more question which says So first of all, just tell me which kind of this pump is. This is a reciprocating pump. It is saying velocity of water in the delivery pipe is V. Where is the delivery pipe? This is the delivery pipe. This is the V. Water in the cylinder is, this is the cylinder. So here in the cylinder, water is V. The area of the cylinder is A. I am writing here A. The area of delivery pipe is A. This is small a. The radius of the crank is R. Crank means here, this one. This is our R. And it is rotating with the speed of W. We usually say omega, but here W. Find the expression for the velocity of the water in the delivery pipe. So you need to find this V, small v. Velocity for this V. Assume that the water is incompressible fluid. Find the position of the crank and apply the continuity equation. See, what is this continuity equation? The volume of water here will be equal to the volume of water here. So we usually say AV will be equals to AV. This is the continuity equation. And for this V AV divided by A. This is the expression. Okay, so these are the options we need to find out. So from here we can see we need to find out this V first. What is this V is? So V is the velocity of water here, and this velocity is coming from due to this like piston. It is going in, coming out. So due to the motion of this piston, this velocity is being generated here. And we can see, we can take, let's say, delta x. It is the distance this water is rotating. So this V, velocity of water, will be dx by dt. Right? Now this x here, if it is rotating like from here to here, let's say this. So this x and this x will be equal. So here what we are doing, we are connecting this x to this speed of this crank, or we can say rotation of this crank. And if we just use the trigonometry, so I'm just plotting here, let's say this is our R, this is the position of crank, and I am taking like this as x, and this is our theta, and this is our R as well. So this x will be how much? This x, I'm writing here, this x will be R minus, means total R minus this distance, and this distance will be R cos theta. So theta is a particular angle at a particular side, but from the rotation we can take it as omega t. Omega t will be equals to theta, so we can write this as R equals to R cos omega t. And if we put this here, we will get V equals to d by dt into R minus R cos omega t. R is constant, so the change in R with the time will be 0. So our V will be like this. R omega sine omega t. So this will be the differentiation. And if you put this back in this equation, you will get smaller v as a by a r omega sine omega t. And this is the r sine omega t v. This is the expression. So this expression is representing the velocity of water in delivery pipe. That is the v. Yes, B, we cast right. B is the correct answer here. Okay, we have a last question which says, which of the following Reynolds number is a perfect range for laminar water flow in a pipe at a room temperature? And these are the options. Simple question, nothing to solve. Zero, 2000, 4000, and infinity. So in this particular range, in this particular range, in this particular range, what kind of flow we have? This is the Reynolds number. With increase in the Reynolds number, how the flow of water changes? Among flow, laminar or turbulent visible? Which flow is good? Depends on your application. See, have you done one particular activity while giving water to the plants, or while like what else you do? While cleaning your vehicle, cleaning your bicycle, cleaning your car, or like two-wheeler, have you used the water with pipe? So sometimes what you do, you have a pipe, you just hold it right way. So the flow of water is so smooth. So smooth, it means it comes by layer. And when you just have some pressure at the mouth of the pipe, you do one thing, you just make it, the area, you just close it down, and due to this close it down thing, there is a high pressure from the backward, and this pressure at the forward increases. So in this condition, what happens? This flow of water become from smooth to the more random kind of, like it go from here to there. So that is a turbulent thing. So from this layer by layer to the turbulent flow, the application does not depend which is good or which is not good. But yes, when do you use which flow, when do you use which flow, which requires based on your application. It is like if this is pipe and water is coming very smoothly this way. This is the our laminar flow. And sometimes what happens, this is things, water comes this way, this goes like this. This is our turbulent kind of thing. So with the low Reynolds number, we have laminar flow. Then it become mix. Then we have turbulent flow. So it question is asking laminar flow. It is 0 to 2000. Yes, correct answer is B. Just try this at your home. You will understand the flow of water. It is the property of water or property of flow. So yes, we are done. We will meet next Friday, this Friday only, coming Friday at 6 p.m. And that will be the second last class. And in the next week, that will be the final class, 12th. I might take one more extra class. So in that class, I will cover things which are other than this particular subject or particular course. I will explain other things which we have not covered in this course. So that will be taken on the next Saturday, 6 to 8. So you will be informed by this NPTEL platform only. So just keep an eye and be regular. Thank you.
Sir, sound is not coming, sir. Okay, sir. Thank you, sir.